Here, this is a video of applications. We're going to look at two different types of applications. The first one is an application to graphs of logarithmic functions. So we are going to find the x-intercept of the function y equals 2 log of x minus 3 minus 3. So let's start with that. So our first example, we have to find the x-intercept. Okay. Notice we could actually figure out the graph of this function by doing some transformation of the basic or toolkit function log of x. Okay. So mainly this function is, well, we take log of x. Let's start with that, even though it's not part of the question. It's nice to link everything together. So log of x minus 3, it shifts everything 3 to the right. So instead of having x equals 0 as the vertical asymptote, now x equals to 3 is the vertical asymptote. And the 2 is doing a vertical stretch of 2, but it doesn't really change the shape of the function, so it would look like that roughly. Okay, this is 2 log of x minus 3, and finally the minus 3 performs a shift of 3 units downwards. So maybe we want to keep track of some points. Maybe the x-intercept here initially is 1 0. After that it gets moved by 3 to the right, so it gets moved to 4 0. And then 4 0 will be sent 4 units down, 3 units down, so to go to 4 minus 3. So we see that we're going to end up with a different x-intercept, okay? And this is what we want to calculate here. So how do we find it? Well, we equate the function to 0 and solve for x. So here, let's try to have only log on one side and with nothing in front of it, so I can send the 3 here. And here I have two options. I guess I could send the 2 as an exponent, but maybe it's just easier to send the 2 on the other side by dividing by it. Okay. And then I could just convert that to an exponential equation. So 3/2 is the exponent to which I raise 10 in order to get x minus 3. And finally we get that x is 3 plus 10 to the 3/2. Which makes sense, by the way. So I didn't write it here, but this is still the same. The vertical asymptote is still the same. So my x-intercept is slightly above 3, well, or above 3. So I can see that it's 3 plus something is above 3, which makes sense. If you calculate this is actually pretty large. It's 34.62. Okay, so the x-intercept is is 34.62, 0. So this is, as you can see, it would be actually way further down on the x-axis. So this graph is not up to scale, but at least you've got some features of it that are illustrated. Vertical asymptote, and actually two points. One point which is the original x-intercept that got transformed, and then this other point which turns out to be the new x-intercept. So this is finding the x-intercept of a logarithmic function. Okay, so it involves solving, of course, a logarithmic equation. Second example, we've got an account that has $100 and it grows by 9% each year. How long will it take to have $1,000 in the account? So then, first thing is you have to figure out what your model is. Okay, so in this second example, so here the A of t. Okay, so this is the amount in the account after t years. it's important to define what your functions actually mean. I won't be able to guess, like on a test, if you write a function without describing what the variables actually mean and what the function actually means. So it's $100 initially, and then each year, okay, we're gonna multiply that by 1.09, okay, 109%, and that's going to be raised to the power of t because we do that every year. Okay, so this is our model. Okay, so first step, establish our model, and so we need to solve here. We want to solve when the account will have $1,000 in it. So we've got this exponential equation to solve. Okay, so we could do different things, but you see the constant is in the way of the is in front of the exponential term, so we're going to send it on the other side. Okay, and here this is like of the form b to the x equals to c, for example. Okay, and I need to solve for x. So I could do two things here. I could take logs on both sides, or maybe just convert this to a logarithmic equation. So t is the power to which you raise 1.09, sorry, in order to get 10. So this is what t is. So it's log n base 1.09 of 10, and then we can use a change of base formula to establish the value of t. So this is change of base formula. And if you calculate this, you are going to get you're going to get 26.72 years. Notice, and this is just a coincidence, that we got log here, we got a log n base 10 of 10. That's actually 1. So that number is also equal to 1 over log of 1.09. And log of 1.09 is not something we can figure out without the use of the calculator anyway. So 26.72 years.